Okay, so today we're going to start logistic regression, and we're going to here's logistic regression, and hopefully we'll finish it in 3 lectures so that we can have a review here on the day before the class before our exam. At least have a good chunk of that class be review. So I just want to remind you, you have 2 bonus opportunities. You don't have to do them, but survey 3, I mean, you might as well do that. That takes 2 minutes, and it's kind of fun. And if you want to get familiar with R or get a little familiarity with R, this one is very straightforward, and but you know, it takes probably somewhere between a half hour and an hour. But it's very useful. Okay. So let's go to our document camera, and we're going to start logistic regression. Well, what is logistic regression? I say it's a regression model for predicting all or nothing outcomes. So our dependent variable, our y variable, is a binary 0-1 variable. If you look back at our the organization on page 183 of our predictive methods classified by type of x and y variables here. So far, our y variable has been quantitative. We've looked at, regression with a single x, multiple regression here. We've looked at categorical x's, predicting ANOVA, predicting quantitative y's. We've had, certainly we've had binary, we did both, categorical and quantitative, predicting quantitative y's, but all of our y's have been quantitative. So we're moving here, right now, to categorical y's. Y's we're going to be predicting 0-1 outcomes like, are you going to pass this course or not? Or, well, you know you're going to pass. Are you going to get an A or not? Are you going to get an A plus or not? A yes or no outcome, okay? As opposed to predicting what your final score would be. That would be a quantitative outcome. So lots of times we're just interested in yes or no outcomes. Are you going to live or die? By the way, did you see, has anybody started the survey yet? The survey that's due, the bonus survey 3? One of the questions would you rather know when you're going to die or how you're going to die? Actually, those wouldn't be binary. When you're going to die would be a quantitative in time. How long from now would you die? And how you're going to die would be multiple categories or not. A logistic regression question would be something like, are you going to die by violent means or not? Something like that. Yes or no. Okay, so that's where we're at right now, and it's very, very useful. So, so far our y variables have all been quantitative, but what if the y variable just has 2 outcomes? What can we do then? What can we do? I mean, think about it. If you have a regression equation, you're predicting, you have some quantitative x, predicting just a 0 or a 1, how is that going to work? Well, what we really are going to do, what we're really going to do, the best we can do is to make a model that predicts the probability of, let's say, of survival, life or death. Often these, I see these all the time in medical data, predicting survival, whether you're going to live or not, given a set of conditions. All right? So usually, so it's a 0-1 variable, and 1 you could say is success, and you could say 0 is failure. Okay, but success doesn't necessarily have to be a good thing. You can code these, it's just a binary variable. You can code them either way. Like the probability of death, you could say, if code death is 1, and not dying is 0. All right, so here's a data set that looks at 55 students, randomly selected from some Midwestern university, And it looks at whether or not, trying to predict whether or not they got into med school, got accepted to med school, that's a 0-1 variable, based on a number of different variables. And one of them we're going to look at right now is based on their biological science score on the MCAT, which ranges from 0 to 15. Now, these students got between a 6 and a 14, and we say if they didn't get it, and it's a 0, if they did get it, and it's a 1. All right? Now, you just see a single dot here, but there, for example, there are a lot more. We'll look at the real data set here, because there weren't just 2 people in each of these categories. There's 55 of them all together. All right, and why don't we just do that right now? So let's just go to the computer, and you can look at this data set by typing in istix.net/Eiermann, and then choose the data set that's the medical school data set. All right, so now let's go to just a scatter plot here. And here's our variables. We can choose on our y variable, our x variables, our predictor variables. Here we're going to choose biological science score, predicting whether or not they get accepted to med school. And let's just increase the jitter so you can actually see, create a little jitter around that so you can see how the different points. So for example, there's 2 people in this, 2 students who got a 6. That's a really low score on that biological science score, and they didn't get into medical school. And here there were, let's see, maybe I can't really see. Let's see, more jitter. Okay, so here there were 4 people who got 12s, and 3 of them got in, and 1 of them didn't. So if you look at the regression line, what is that doing? Well, one way you can think about it is as estimating within each of these vertical strips. Let's make a little vertical strip here. Estimating the average. So here they both got 0s. So this little horizontal line here, this horizontal line indicates the percentage of people who got in. 0 got in with a 6, 0 got in with a 7. Let's see, with the 12, it looks like there were 3 up here, and 75% got in, 0.75 with the 12, etc. And so that's what it looks like. And so you can think of if we just did ordinary regression, predicting probability here, we'd just do the best fitting line to minimize through these horizontal strips here. But there's a number of problems with that. One is that you see, as you see in your notebook, that you're going to get probabilities that extend beyond the limits. Probability ranges between 0 and 1, and here you're going to get probabilities more than 1 for reasonable, for people who got a 14 and a 15, it would predict more than 100% chance of getting into med school. And here, for these people who didn't get in, it would predict a negative probability. So clearly there's something wrong with that. Also, as you can see, the errors, we can't use our ordinary methods because our errors aren't normally distributed, our prediction errors. You either get 0s, they're just 0s. Our actual values are just either 0 or 1. Okay, so how are we going to deal with that? Let's just look at let's go back to our document camera. And the first thing that we see, like I just said, if you look at 10, it predicts a pretty reasonable, just using our ordinary regression, it predicts a pretty reasonable probability. What would that be? Well, we'll just use this equation here, and this says the predicted acceptance probability of being accepted is negative 1.263 plus 0.1848 times the score. So for a 10, that gives us a 58.5% chance of getting accepted. Well, that's reasonable, but when look, it's going to give us a negative probability for 6 and over 100% for 6. This will give us negative 15.4%. Negative. That's sort of depressing, right? For people who, those two people who got a 6, if we gave them this regression equation, you have a negative chance of getting into, that doesn't even make sense. It would be sad. Okay, and these people who got a 14, it's over 100%. You do the same thing, stick a 14 in, 1848 times 14, and you get 143.2% chance of getting into medical school. So that's crazy. These two don't make sense. And so we're going to have to do something different. Remember, probabilities range. Probability is always between 0 and 1, or in percent, or between 0% and 100%. Okay, so we've got to do something different, right? Now let's look at it. So let's turn the page, and please stop me, ask questions, because a lot of you, this is really unfamiliar territory to a lot of people. How many people have seen logistic regression before? Raise your hand. Just one person in here has seen logistic regression before. How many people have even heard of logistic regression? Raise your hand. Not very many people. Well, some people have heard of it. Okay, it's really pretty common, and it's going to take some getting used to, so please ask questions. Okay, so how can we fix the problem of getting probabilities outside that 0-1 range? Well, we can fit a curve instead of a line. So instead of fitting a line through each one of these points is the average of the vertical strip. That's what these points are, and we can fit a curve through them, like the one below. Okay? Here, I'll show you. Let me show you on the data program again, because I think it's nice to look at and you can explore this yourself. You can look at a 0-1 scatter plot here. And again, we have acceptance as our y, that binary yes, no, and now we're going to use the biological science score here. And we can add some jitter, so you can see, and then we do that regressogram, and there you see, those are the points that you see in your notebook. I put a little point for each one of these. And now, here's our ordinary regression, and that has problems we just saw. So instead, we're going to fit this S-shaped curve, logistic regression. So let's look at the equation of this curve. That's what we're going to do now. Okay, so let's go back to our document camera. And, all right, so there are many curves with this S shape, right? We want an S-shaped curve because we don't want to extend beyond 1 our predictions. For the probability of getting a 1, we don't want to extend beyond 1, and we don't want to go down below 0, so we want this S-shaped curve with the limits at 1 and 0, like that, within those two, that range. All right, now, there are many curves with S-shape is similar to the one above, and the most commonly used one is the logistic curve. That's what this is, but basically, any curve, well, any equation of the form what? Y, this is our y-axis, is equal to f of x over 1 plus f of x, as long as f of x is positive and increasing, like that. Because that, any equation, of course, you can see if it's the limits, if f of x can't be negative, you can see that's always going to be between 0 and 1, because the numerator is always smaller than the denominator. And here, okay, so here's the logistic, here's the f of x we use. See, e to the beta naught plus beta 1x for one quantitative, one predictor variable predicting a binary over 1 plus. Another way to write that you'll often see is this way. So here's the equation of the logistic curve for simple logistic regression. 1x predicting a binary y. These are equivalent. Where P is the probability of a success. So the probability of a success follows this curve. Okay? So this is P right here. Probability of success. Probably I should write P there. Okay. So let's just make sure. Can this equation ever yield a probability greater than or equal to 1? No, we said no. It can't, and you can look at this one. Of course it can't. Because why? The numerator has to be smaller than the denominator. E to the beta naught plus beta 1 x is always going to be smaller than e to the 1 plus beta naught plus beta 1 x, right? This is your numerator. It's always going to be smaller than the denominator. And can it ever yield a negative probability? No, because e to the beta naught plus e to the anything is always greater than 0. No, because e raised to any power, right, is greater than 0 for all x, no matter what x is. If x is really tiny, right, the limit is what? If x is a really, really small number, so as x negative number, or really, and what I mean is a really, really giant negative number, you'd have 1 over a giant number, so it would be the limit as x goes to negative infinity, v to the x is 0. Negative infinity, that's what that says. So it has to be between 0 and 1, which is good, because we want our probability to be between 0 and 1, right? Does that make sense to everybody? Not if it makes sense. Okay. All right. So now it has two nice features. The one we just talked about, it yields a probability between 0 and 1. And the other nice feature is this, that we can transform the variable p to a form to something called the log, natural log of p over 1 minus p, which is linear in x, allowing us to continue to use many of the methods we've been using for linear models. So if we take the log, this is called the odds. Success over failure is your odds. When you say you have 4-to-1 odds, it means 4 times as much probability of success as probability of failure. So this odds is called your odds, and the log of the odds is a linear equation. Okay? And so the logistic model has these 3 equivalent forms that you'll see all the time. This is called the logic or the log odds, natural log always form, and this one is a line. You can see it's the equation of a line. You have an intercept plus a slope times an x. So this is our linear form, and it goes from negative infinity to positive infinity. All right, and then when we translate it into an odds form, this right here is the odds form, and this, if you can see, is an exponential curve. It's e raised to the beta naught plus beta 1x. So this is an exponent, this is a line, and now you have an exponential curve here. It's going to go, the smallest it can be is 0, and it goes up to positive infinity. Keeps getting steeper. All right, and then this is our probability form, and this is this S-shaped curve. And it has its limits. The smallest it can be is 0. Then it gets real steep in the middle, and then it flattens out again at 1. It never reaches past 1. All right, so those are our three forms. And you can see that here, if you exponentiate both sides of this, you get e to the beta naught plus beta 1x. And here, going between these two might be a little bit more difficult. Well, look, let's write it down first. So our odds are defined. So you want to go from the odds to here is p over what? 1 minus p. And now probability form, the probability form is, I'll write it up here, p is equal to the odds over 1 plus the odds. So you can go back and forth, and even though this looks really messy, it's just because the function's so messy. It's a few algebraic steps. It's really pretty simple, and but it looks awful. So why don't we just look at this later? You can transform back and forth between these, and why don't we just familiarize ourselves first with how you calculate odds and probabilities and log odds, just with numbers, and we'll get a good feel for it. Then it'll be very easy to see this. All right, so let's do that. So odds and log odds, because I'm sure you're not used to this. Unless you're a gambler, you probably don't think in terms of odds. You think in terms of probabilities. Okay, so the log of p over 1 minus p is called the log odds, because this is defined as the odds. Okay, success over failure. And of course, they have to add to 1. The total number, they have to add to 1. There's no other possibility. You either have a success, in situations where you're just saying there's two outcomes, success or failure. They have to sum to 1 or 100%. Okay, so let's look. So if you say your odds, for example, is 4, this means the probability of your event occurring is 4 times more than the probability of it not occurring. And people call that 4 to 1 odds. So let's just do that. So if your odds are 4 to 1, what's p? Okay, how can we think of this? The way that I think of it is this way. I think, okay, so the odds 4 to 1, this is an easy way for me to think about it, means you can think of it as proportionally, it's 4 to 1. So you can think of it as means there are, I can think of it as 5 outcomes, right? 4 plus 1 equals 5 outcomes. 4 successes and 1 failure, right? It's a 4 to 1 ratio, so I think of it as just 5 outcomes. 4 to 1, okay? And 1 failure. And so then it's really easy to go from odds to, so your odds are equal to 4 to 1, all right? So just think of this right here as the number of successes, right? And this right here is the number of failures. So those are your odds. So your probability then is your success, 4, over what? The total number of outcomes, 4 out of 5. Does that make sense to everybody? And doesn't that make sense? What are the odds? What if you have 1 to 4 odds? What's p? Let's do that. What if your odds are equal to 1 to 4? I'm going to just draw this like this. Well, what if that? Then what does it mean? It means 1 success over 4 failures, right? Doesn't it? 1 to 4? I see blank faces. So wouldn't that mean, what would your probability be? One success over what? How many outcomes total? 5. So it would be 1/5. So let's do the next one. What if your odds are 1/2? Your odds are 1/2. So odds equal 1/2. Then what's your probability? Think of this as your success. 1 over what? How many possibilities are there? 3. So your probability is 1/3. Doesn't that make sense? And then going the other direction, you'd say 1/3 over 2/3. Well, that's 1/2. And what if your odds are 2 to 1? If your odds are 2 to 1, well, then what's your probability? You write it in. What is it? 2 to 1 odds. More ways to, twice as many ways to succeed as to fail. So it's, your probability is 2/3. 2/3 of the time. It's a 2 to 1 ratio between your success and your failures. Does this make sense? Nod if it does, so I know. That's how I like to think of it. Just you add that numerator and denominator, that's like your total, and then your success is just that numerator over that. Your probability is just the numerator over that. Okay, so if your odds are 2/3 or 2 to 3, so your odds are 2/3, then your probability is success over failure. Your probability is success over the total, so it's 2/5. You got it? Good. I see lots of nods. Great. All right. So now let's move on and we'll fill out this chart, which is what you have to do in your homework. This chart down here. And let's just make sure we've got this down. So the probability ranges from 0 to 1. It's confined within that, so it has that weird S-shaped curve. Remember? It has to go like between 0 and 1. That's our probability. And so that's why we have to write an equation for a curve like that. And we have the equation that works for us, because it's linear and the log odds, is this function, e to the beta naught plus beta 1x, because when we take the log of that, we get a linear function over 1 plus that. So that's the equation for the curve we're using. Then, okay, and then our odds range from 0. It's this exponential curve that looks like from 0 to 1, and there our odds are equal to what? E to the beta naught plus beta 1x. And then our log odds are just a linear equation, this log odds from -infinity to infinity. And that's where we have this really nice, easy linear equation. So that's what we're going to be fitting parameters to. We're going to be fitting the betas to this, because it's just a linear equation. And we get beta naught plus beta 1x. So that's what it looks like. All right, well, you'll see this if you work. Let's just fill out this chart. We'll give you a good feel for it. All right, so let's just start anywhere. It doesn't really matter. 1 out of 100. Okay, so if your probability is tiny, only a 1 out of 100 chance of success, well, then there's 99 out of 100 ways to fail, right? Out of 100, one is, they have to add up to 1. Everybody understand that, right? If there's 1 out of 100 ways to succeed, then there has to be 99 out of 100 ways to fail. And they have to add up to 100, so, okay? I mean, they have to add up to 1. They have to add up to 100 over 100, sorry. They have to add up to 1, or 100%. So, we've got that. Now, what are our odds? Well, we said p over 1 minus p. So p over 1 minus p. And so you might write it at first like p over 1 minus p. So that would be what? 1 over 100 over 99 over 100. But do you see that's the same thing as just 1 over 99? One way to succeed and 99 ways to fail. So we don't have to do that, right? Those just cross off. Okay? We can simplify. So it's one success, since we're out of 100, 1 over 99. Does that make sense to everybody? Okay. So those are our odds, 1 out of 99. All right. Now, you can't do the last one in your head. We have to log odds. We're going to have to use your calculator. So let's do that. And so we'll say the log, the natural log of 1 divided by 99. All right, and we get a negative number, negative 4 point, etc. Why don't we just round it to negative 4.6? All right, now why don't we see what happens when we just go, this is when we just switch p and 1 minus p, which is, I made this symmetrical. So now instead of having only 1 out of 100 ways to succeed, let's look at 99 out of 100 ways to succeed. They're totally symmetrical here. All right, see how now, if there's 99 out of 100 ways to succeed, there's only 1 out of 100 ways to fail. So you see how these are just flipped, right? Does that make sense? And now, what do you think the odds is here? Instead of 1 out of 99, what do you think, instead of 1 to 99, what do you think it is? It's 99 to 1. Does that make sense to everybody? Those are your odds? Okay. And now, does anybody know, does anybody know what this would be? If you're familiar with logarithms, you might know what this would be. Does anybody know? We're taking the log, you know how you can look at it? Well, you can think of it as we're taking the log of 1 over 100. Oops, 1 over 99 here. Excuse me. The log of 1 over 99. Do you know that's the log of 1 minus the log of 99? And we got negative 4.6. And here, we're taking the log of 99 over 1. So let's try that. The log of 99 over 1, which is the log of 99 minus the log of 1. What do you think it's going to be? By the way, the log of 1 is just 0, too. So do you see how, what do you think it's going to come out to be? Want to guess now? Look, if you do 5 minus 3, you get 2, and 3 minus 5, you get negative 2, right? So what do you think I'm going to get here? I have log of 1 minus log of x minus y, and here I have y minus x. So what do you think I'm going to get? Say again? 4.6, is that what you said? Mm-hmm. It's just going to be the opposite. Does everybody see that? Mm-hmm. Okay. And let's make sure we do. Let's make sure we get the same thing. Let's write it in and make sure we get it. So we'll do it, and we'll say log of 99 over 1, which is just the log of 99. Oh, what did I do wrong? Oh, I see I did. Okay. Log of 99. You see how we got the same thing? Just the opposite sign. All right? Okay. So that's what we've got here. The idea. Now, just to get you, I always like to work with numbers just to make sure that you know how this looks. And so let's just fill out the table below. So I'm giving you these different probabilities here. You can see it's symmetrical, around 50%, 50-50 probability, all the way down to 1 over 100. So let's look at this, and let's just fill it out. So we can start anywhere you want. I don't care. We can just start here at 3/4. Okay, so if p is 3/4, then 1 minus p, this is success, 1 minus p has to be 1/4. And then what would your odds be? Your odds would be what? 3-to-1, right? Wouldn't your odds be 3-to-1? The successes over the failures, 3-to-1. 3/4 over 1/4, which is 3-to-1. And then your log of 3 would be what? Let's look. So the log of 3 is 1.0986. Can we just round that to 1.1? Is that okay? All right, so round that to 1.1. All right, now let's look at this. It's symmetrical with this one. So let's do this one now. What's that going to be? Well, if P is 1/4, 1 minus P will be 3/4, and your odds are going to be what? Instead of 3-to-1 here, they're going to be 1-to-3. And what do you think this is going to be? This is the log of 3, and this is the log of, this is just going to be the opposite, right? We can do it, but can you see that? That's the log of 3 minus the log of 1, which is 0. And this is the log of 1, which is 0, minus the log of 3. They're always going to be reciprocals of each other, right? Okay. I mean, the log of x over y is equal to the log of x minus the log of y. So y over x is just going to be the opposite. All right, so we've got that. And should we do another one?
Can we do the steps
for this? For which one?
For like all the boxes? Like I'm a little confused.
Sure. I bet you it will snap in a minute into place. Look, where do you want? We can start anywhere you want. Should we just do this one? Start here? Sure. Okay, so how am I doing this? 1 over 100 is your probability of success. There's 1 out of 100 for success. So how many would there be out of 100 for failure? If there's 1 chance in 100 that you're going to succeed, how many chances are you going to fail?
99 divided by 100?
Yeah, that's all it is. Like if there was 1 out of 100 chance, that means you have a 99 out of 100 chance of failing. So your 1 minus P is 99 out of 100, you see, right? Those numerators have to add up to the denominator, which is your total number of outcomes. Now, your odds are just the odds. If you wanted to do a P over 1 minus P, you have 1 over 100 divided by 99 over 100, and the hundreds cancel out, right? So it's just the times since they're both out of 100, it's just the number of successes over the number of failures. So it's just your numerators. Do you understand? Does that make sense? Okay. So your odds are just going to be the ratio of those numerators, because it's just 1 out of 100 over 9, so that's 1 out of 99. All right. Now, to get the log of the odds, what are we going to do? We're just going to say the log. Let's say you don't know anything else. You can always 1 divided by 90. Whoops, look what I just did. 1 divided by 99, right? Right? Now that's going to be a negative number because, we'll see, negative 4.6, all right? Okay? So that's negative 4.6. Now I want everyone to do this column, because it's just do it, just to make sure it's totally symmetrical. So just take a minute to do that while I take a drink of water. And your homework is going to be filling out one of these charts for sure, because believe me, I could stand up here forever and teach it too, but you really have to play with the numbers, and same with that's how you understand things. Okay, so what are we doing here? We're just saying, okay, 99 out of 100 chances of succeeding, but there's still that 1 out of 100 I could fail. So there's the 1 out of 100. My odds are 99 to 1. And now my log odds are going to be 4.6. It's totally symmetrical around a 50-50 shot right here. And this, we'll do this one next. But if you want to check that, you could just say, okay, the natural log of 99. And that's so always check that these are totally symmetrical, right? Okay. Now let's just do, they're symmetrical around 50-50 probabilities, okay? 50-50 is dead center here. And so what that means, your chances of success, P is a half, 1 minus P is a half, 50-50 shot. It's 1-to-1 odds, 1-to-1 odds. And here, what do you think in the log of 1 is what? If you forget, the log of 1 is 0. Because e to the 0 is 1. Anything raised to the 0 power is 1. So there it's symmetrical around that, okay? So when you're in the log odds, we can fill out the rest of it quickly just to see. Might as well, or do you want to do it on your own? Do you want me to do it, or do you want to do it on your own?
Let's move on.
Move on. Okay, we'll move on, but I just want to show you one thing. You see, look at this. If you have a 50-50 chance on here for the log odds, 50-50 would be right there. Okay? And here, it would be, here it would be right in the middle here, where this is, and here it would be right in the middle here. Okay? All right, let's move on. Now we're going to make predictions. And thank you for stopping me, please. It benefits everybody when you ask a question. So please, and it helps me, makes me happier. So back to the predicting the probabilities. All right, so now we're going to use the log odds equation because we want to get those probabilities, and we're going to get a linear equation in the log odds. Okay, and the computer's going to estimate these betas, the beta naught and the beta 1. They're going to estimate these two parameters. And that maximize, usually we did it by least squares, but we're going to do something called maximizing the likelihood of obtaining our particular sample, and that's called maximum likelihood estimates. In this case, these are not the same as our least, well, we can't do least squares estimates here. We'll explain more about that later, because our errors aren't normally distributed at all. They're just zeros. Our outcomes are zeros, the actual outcomes are zeros or ones. You either did or you didn't. And the predicted, so the actual minus the predicted is not going to be normally distributed, because the actual is always just either a 0 or a 1. So later when we do inference, I'm going to explain maximum likelihood estimates more and how they're different from the least squares when we do inference. But for now, let's just understand how to make predictions here, what the coefficients mean. All right, so you get this output that's going to approximate, in our test statistic with large samples, is going to be a chi-square statistic. It's actually something called the deviance. We're going to get this little ANOVA table. We'll talk about this more, like an ANOVA table, but instead of sums of squares, we are going to be trying to minimize something called the deviance, or maximize. We're going to get this deviance column here instead of the sums of squares. And the deviance, the sums of squares model is going to be similar to this. But for now, that's to come. For now, let's just look at this, all right? So now, when we do the logistic regression, here's our equation, the log odds equation. We're just looking right here. Here's our intercept right there, and there's our slope right there. And it's in the log odds as y, and our biological score is our x. So this is what's given to you. But how do we get to the probability? Okay, so I explain it here, but let's just see how we work it out, okay? it's just the usual. We're going to anti-log it. And then we're going to go, once we get the odds, we're going to use odds over 1 plus odds to get our probability. So let's go ahead and do that and make sure it makes sensible estimates. Like before, when we had that other equation, it wasn't this. Well, it was when we started off, it gave us crazy stuff. This one, this is a completely different equation. It was just a linear equation trying to do probability, not doing probability not doing the log odds. Here we just, and it gave us nutty, gives us estimates that are way outside the range. These are the estimates we got. Now we're going to get much better estimates by using the log odds equations. All right, so let's just do it. All right, so we're going to start off, we're going to plug 10 for BS, and that will give us not our probability, it's going to give us our log odds. So our first step is just to get the log odds, so we'll do that. So we'll get the log of the odds is equal to negative 12.2 plus 1.276 times 10, all right? And I did that, and I got 0.56. But that is the log of the odds. I want to know the probability. If somebody gets a 10 on their BS score, on their biological science score, I want to know the probability they'll get into med school. This is just giving me the log odds. So now I have to go to my next step, which is the odds, right? So now I'm going to go to the next step, and that will be the odds. So how do you do that? You want to anti-log both sides. So you'd raise each, exponentiate each, so it's E. That will give me the odds, right? That'll give me the odds is equal to E to the what? E to that. Right? I'm raising, just exponentiating both sides. All right? So I get odds equals E to the 0.56, which is 1.75. Now that's the odds. Now you can think of that as, to get P, is our third step. And so to get the P, the third step, which is right here, what should I do? Well, how would you do it? Just imagine, put a 1 down there. It makes it much easier. So now you know how to do that, right? It's probability. Think of this as success and that as failure. Think of that as success and that as failure. So your probability would be success over the total number. Total, the total, success and failure. That's what you're doing here. 1 plus 1.75. So that's 1.75 over 2.75. I don't have that written down, unfortunately, so I'm just going to do it here. So it's 1.75 over 2.75. So it's about 64%, 0.636. Does this make sense? So that's about 64%. That's closer, really, to the percentages we saw. Okay. All right, so that's our answer for that one. Now we can do the next one. So we can do them all that way. So we'll just do it and make sure. I just want to make sure we're not going to get any negative probabilities or probabilities over 1. So now we'll do the next one. We start with the log odds. So you say the log odds, and we're doing exactly the same thing, negative 12.2 plus 1.276. But this time we're plugging in a 6, so we're going to get something smaller. In fact, we're going to get a negative number. So we get negative 4.544. Now my next step is then to do the odds. And I just exponentiate it, both sides, e to that. So what you're really doing is, okay, so it's e to that, e to the negative 4.544, right? I do that, and I got a very small number, 0.0106. And now to get the probability, I'll put over 1 just because it helps me. To get the probability, I'm just going to say that's my success in the total number of outcomes. Odds over 1 plus odds. That's your odds. Whoops. 0.0106 over, I'm just going to add 1 to that. So it'll be 1.0106. And what is that? I didn't do those last steps. 0.0106 divided by 1 point. It's going to be a very small number. 0.0106. And, what is that? 1.05%, okay, which is equal to 0.0105 rounded. 1.05%. It's not 0%. Okay, do you want me to do the last one or not? Might as well? No? How about I give you the answer and you see if you can get it yourself? Is that good? Yeah.
So for the one that you put under the answer for the odd part, is that just like to remind you that there's like a bot, like it can be interesting?
Oh, yeah. I mean, this is just a formula, but I'm just thinking like when we did it ourselves, naturally, 2 to 1 odds, we knew these two together, the total number of outcomes. So it's very natural.
So it's you have more odds than you have outcomes, or success than you have outcomes?
Here it's saying you have more successes than failures. If you have odds greater than 1, that means that you have a better chance.
Yeah, I was thinking of the wrong part.
Yeah. So it's just, you don't have to do that, but that just makes sense out of it. It's like, think of these as your successes and your failures. So if it's anything greater than 1, your successes outnumber your failures. You should get over 50%. And you saw that in that chart here. If your odds are greater than 1, right here, that means your probabilities are going to be, at 1, it's a 50-50 shot. And log odds, 0 is a 50-50 shot. So if your numerator is bigger than your denominator, for the probability, yeah, it makes sense. I mean, you can solve it, like here I did it algebraically, but it's just easier for me to it's just easier for me to see it intuitively. I'm doing the same thing here, but going back and forth between them all, but it's just easier for me to do it intuitively, sort of. Okay, not in general, but you should go back and look at that if you want. It's the same thing. Okay, so now you said you want to do this on your own. That's fine. And I'll just tell you what you get. You get 90. The answer for this, the probability is going to be 0.9965. Very high probability, but it doesn't go over 100. Okay? Is that good? So how about this one? At what score do you have a 50-50 chance of getting accepted? What would that look like? How would you do that? 50-50 is a probability of 1/2, right? So what would your odds be? Your odds are what? P over 1 minus P, right? Aren't your odds 1 to 1? One half over a half, or 1 to 1, right? And so then what's your log odds? Your log odds would be 0. All right, so now, so what score would give you the log odds of, well, you have to go back to your equation. Your log odds, you want that to equal 0, and your log odds are negative 12.2 plus 1.276 times your score. So you want this to be 0 is equal to negative 12.2 plus 1.276 times your score. So your score is going to equal what? 12.2 divided by 1.276, solving for the score. So that's 12.2 divided by 1.276, and it's 9.56, almost 10, between 9 and 10. Does that make sense to everybody? Okay, so let's move on. All right, so now this is what people sometimes have difficulty is like interpreting the slopes in the log odds equation. What do those slopes mean, those slopes in the log odds equation? All right, so first of all, what does the sign of the slope mean in the log odds equation? So here's our log odds equation. Odds is P over 1 minus P, success over failure. And so we get, here's, and this is a graph of, P. This isn't a graph of the log odds. This is a graph of your S-shaped curve, which is P over, which is E, we just did E to the beta naught plus beta 1x over 1 plus that. Okay, so here's your curve. It's 0. And this is 1, and what's this, 0.2, 0.4, 0.6, and 0.8. Okay, so let's think about what it means here. So it tells us whether the probability P increases or decreases as x increases. That's the sign of this slope here. So if your probability as x increases, this is x, as x gets bigger, this will be a positive slope or a negative slope, right? If as x gets bigger, your chances, like this could be getting into med school and being drunk or get how much you party or something, let's say. Then the more you party, the lower your chances are of getting into med school. It would look something like that. All right? Something that's going to make it less likely to get it. All right, and then, so that's, and then the magnitude of the slope determines the steepness of the curve. And the steepness varies, right? The steepness varies. Say, for example, and this makes sense, like on your ACT scores, did everybody here take ACTs? Or what did you take, SATs? Raise your hand if you took ACTs. Just want a standardized test you took. Okay, so if you're in the middle of the curve here, like probably for U of I, that's like somewhere between, 28, 29, or somewhere in there? It's going to make a big difference whether you get a 29 or a 30 or 28 or 29, 27, 28 in the middle of the curve getting into U of I. But up here, whether you get like a 34, a 35, or a 36, not going to make, you're already pretty much in. And down here, if you got like really low scores, I don't know, 12, 13, 14, 15, you're probably not going to get in. So a little difference down here doesn't make much of a difference, but you see how it makes a huge difference in the middle of the curve? Does that make sense to you? Your probability of getting in? I mean, if you look at those percentiles, you get a 1. When you're way up here, you might increase from a 99%, 98 to a 99 percentile, but when you're in the middle, you're going to make a big jump with just 1 or 2 points. So now mathematically, what does that mean? So mathematically, what do we have here? We have these 3 forms. These are 3 equivalent forms. We're going to be going back and forth between them, okay? And this one is a line, you can see, and this one is a curve. It's an exponential curve, e to something. This is a curve, an exponential curve. And this one, which is the probability form, which is how we intuitively think of it, is the S-shaped curve. Okay, so we have these 3 equivalent forms. This is called the logit form. That's what you'll hear people say, the logit form. This is the odds form and the probability form. And the odds form actually yields the most intuitive and useful interpretation of this slope here. This slope is most easily interpreted in this form. Because so let's look at this. this is this is right here, this slope right here, in the log odds form, okay? If we look at it in the log odds form, it's right here, and then in the odds form, all right? So what does it mean? In the log odds form, it means that for each extra point, this is very easy because it's a linear equation, but it doesn't really make sense. It means that it's not very intuitive. It means that for each extra point in your biological science score, the log odds of getting into med school increases by 1.276. That's not helpful intuitively for me. The log of the odds increases, maybe for people who are really used to logarithms or something, or that just doesn't seem real intuitive. But now let's look at our odds form and look where that 1.276 is. It's right there. Okay, now what does this mean? This means that for each extra point on the biological science score, the odds of getting into medical school are what? Are multiplied. Each extra one, you're going to be multiplied by e to that slope, by e to the slope, or by raised to the 1.276, which is about 3.58. So that's called the odds ratio. It's the multiplicative increase in the odds for a 1 unit increase in X. This means going up 1 point in your biological science score multiplies your odds by about 3.5 of getting into med school. Okay, what is the probability form would say? So, first of all, this odds ratio is e to that slope is the odds ratio. All right? And basically, what am I saying here? When you look at this in the odds form, well, you know what the slope means here, right? It's a line, so you know what the slope means here. But here, it says the slope changes by a fixed multiplicative factor. That's what this is saying. So here you have, and that is e to the slope. It changes by, so I'll just say the slope, what do I mean that? Changes by a fixed multiplicative factor. Oh, multiplicative factor. And that factor is e to the slope. In other words, when you have an exponential curve, it keeps increasing. Like the slope here is gradual, it keeps getting, and how does it keep increasing? It keeps increasing by a fixed multiplicative factor. In this case, it would be for 1 unit of X, it's going to get 3.58 times bigger. And it keeps getting steeper and steeper by that multiplicative factor. That's what it means. It's not, whereas with a line, it's the same slope throughout. For 1 unit increase in X, you go up the same amount. Here, you go up a little bit, then next for one, you're going to go up 4 times as big, and then 4 times bigger than that, 3.58 times bigger. It keeps increasing, right? That's what it means. But then, for this one, what happens here? Here, the slope starts off really, this is what I was saying, it doesn't change your odds much in the beginning, but then it gets steeper and steeper, and it's maximum here in the middle. The change is maximum in terms of the log odds. It's not in terms of this curve. And then it gets really gradual again. I mean, in terms of the probability form. The probability form. See how it's like starts off really, see, it's not a fixed factor. It depends on where you are. So here, in fact, what the slope is, what it is it's going to be beta 1 times p times 1 minus p. So when p is 0, you don't need to really know this, but when p is 0, it's like almost a 0 slope down here. And when p is 1, it's a 1, right, times 1 minus 1. So again, it's about 0. But in the middle, when you have a 50-50, it's maximized right here in the middle. P times 1 minus P is maximized right in the middle. So maybe we should write that. So the probability form, in the probability form, the slope changes depending on what x is. It doesn't for the other two. It has a fixed additive factor here. For a line, it has a fixed additive factor. For a curve, it has a fixed multiplicative factor. But now we have a curve with an S-shaped curve, and it changes depending on x, right? It goes like this. It's very gradual, and it goes really steep, and then it's really gradual again. Or it falls that way. It gradually rises, and then it's steep, and then it's gradual again. All rising or all falling if it was a negative slope. Does that make sense to everybody? Does that make sense? It gradually rises or falls, and it sharply rises or falls, and then it gradually rises or falls again. Just look at the shape of it. It gradually, steep, gradual, or when it's falling the same way. Okay, now let's just do this last page. Make sure we have this because we have to be able to do the homework. All right, so now this last page. All right, so what are we doing here? So now we're just going to look at this slope, right? So in the last chapter, we predicted the odds of getting into med school for someone with a BS equal to 10 to be about 64%. We got the odds, and then we got the percent, the probability. Now, what's the odds and probability if that person goes up by 1 point, right? What happens if that person goes up by 1 point? We were using this equation, I should write it here. We were using this log odds equation, which was negative 12.2 plus 1.276 times the BS. Okay, so all right, so what's the odds and probability? All right, so we're gonna start with the biological score, right? And now we wanna go to the odds. Let's do that. And so with 10, we already did that. We plugged a 10 in, right? And we got this. We plugged a 10 in and we get 1.75. That's given to you right here. That's where the 1.75 comes from. And then we got this probability. Okay, so then we went all the way. We got a probability equal to that, about 64%. Okay, 0.64. Now, what happens if we do 11? Well, with 11, what are we going to do? All we have to do is, if we look up here, you can see what's going on. Instead of a 10 here, you're going to have an 11 here. So it's going to be these odds, 1.75. How are they going to change? They're going to change by multiplying by e to the 1.2, e to the slope. As you go from 10 to 11 here, all you're doing is multiplying, because it's an exponent there. You're increasing your exponent by 1, so you're really you're multiplying by e to the 1.276 there. Right? Does everybody see that? So, and what is e to the 1.276? So that's about 3.58. Maybe I'll just use that. It'll make it easier to see. So this is the fixed multiplicative factor. So all we're doing is taking 1.75. We're going to multiply it by 3 to the 0.58. Okay? And I did that, and I got 6.27. So now what's p? Well, p is going to be 6.27 divided by what? 7.27. 1 plus 6.27. And that is 0.86, or 86%. All right? So all I want to show you is that basically this e to the slope, this factor of 3.58 is how much you would multiply the odds by as you go up 1%, as you go up 1 point. This is going to be exactly the same thing, right? Do you want me to do this one too? Yes or no? For 6? I mean, I'm just doing the same thing. So you have the BS is 6, and I say what? You get this odds here. You get this odds. We just did it on the previous page, and then we got the probability, and it was what? The probability was 0, it's right here, 0.0105. Remember we got that? Now if you go up just by 7, what happens? Well, you're just going to take this and multiply it by 3.58. And that's just going to be about 3 times, a little bit more than 3 times as much. And then your probability would be that over 1 point there, right? Which is about 3%. Okay? So this is just how much you multiply. This is e to the slope right here. It's right there. So that's called the odds ratio. That's what people call it. It's the multiplicative change in the odds. Okay? So you can't talk about the change in the probability because that changes. It's greatest around 0.5, but it varies. So two people have a 2-point difference in their biological scores. So what would you? So the odds of getting into medical school with the person with a 2-point higher score has a what? Which one? Circle one of those. There's actually 2 of them. For each point increase, it's going to multiply by e to the 1.276. So you're going to multiply it and then multiply it again, right? So it's going to be this one, which is the same as that one. 3.58 times 3.58. Right? So just for each point difference, the odds are multiplied by e to that slope that you get in your log odds equation for the variable, e to the 1.276, which is equal. Okay, so what if there was a 3-point difference? The person with the 3-point higher score would be what? It would be 3.58 times 3.58. You should probably not simplify. You should probably stick, you'll get rounding error. It would probably be better in your homework to do 1.276, times 1.276 times 1.2. This. Sorry. How many times? 3 times? So it's e to the, times 3. So you could just do that in your calculator. Okay, and I did that and I got about 46. 46 times higher. Okay. Now, if 2 people have a 3-point difference, how do their probabilities of getting into med school compare? Well, we have no idea because let's look at it. If that 3-point difference happens here, it's not much. Or here. But if the 3-point difference happens here, their probabilities are going to be very different. It just depends on where they occur. So that's the idea. You can't, that's why people talk about the odds ratio, because you can talk about the increase in odds, but you can't talk about the increase in probability changes depending on what the X value is. So you don't have enough information. You can't figure that out unless you know. It's going to be different going from, a score of 6 to 9 than it is from 9 to 12. So not enough info. We don't know. because we don't know their exact scores. It's going to change. Okay. In other words, we know this. We know the odds ratio. That's e to the slope. We know that. But we don't know the odds. We just know the ratio. If we knew the odds, you can get it, but we don't know the odds. We just know the ratio of their odds. If we knew the odds, it would be fine. The odds, probability is just odds over 1 plus odds. We know the odds ratio, so don't get that confused, but we don't know the odds. The odds change depending on x. Odds and probability change depending on x's. But the ratio is the same. That's the point. That's why your people talk about the odds ratio all the time instead of the odds, because you can get that constant odd ratio even if you don't know the particular probabilities. All right, so that's all for today. I should post your homework soon. And thanks for asking questions.